record the lecture.
And you said it's chapter 3 and chapter 4. Which lecture notes does that end with? 8?
So all the lecture notes posted and whatever we covered in class before the Corona break.
So everything that you start with now is not on that test?
No.
Okay, thank you.
Don't worry. You see the test, you will know what's on it, right? Don't be too worried. All right. So today we talk about continuous random variables. If you could, guys, turn off your mics in case you are making any sound, and talk to me as soon as you have questions. Just turn it on whenever you have a question, or type me a note. So, yeah, good. So, continuous random variables. I hope the analogy I'm going to make here will help you understand it. So imagine that you go to a hair salon, and there you have a barber. And then let's say maybe you record how the barber is cutting each strand of hair. You might imagine that each strand of hair is either of the same size for simplicity, or that the barber cuts the hair by some relationship to the proportion of the length of the hair. So the hair is in general from 0 to L, which you can normalize and make it from 0 to 1, which means 1 is the length of the hair, and 0 is where the hair is attached at your scalp. Okay, and then let's say you witnessed 1,000 hairs being cut. And clearly you can see the hair can be cut anywhere from the very base of the scalp to the very tip of your hair strand. So suppose that you observe the following. So you observe that if I just look at whether the hair was cut at 1/2 or below, or at 1/2 its length to 1, and I observe that for this barber, 1/4 of all the hairs cut. In other words, if I look at all the 1,000 hairs intimately, I see that 1/4 of them were cut below 1/2 mark, and 3/4 were cut at 1/2 mark or above. Okay, so you don't distinguish exactly where. Maybe the cut happened somewhere here, or maybe it happened somewhere here, but all of them correspond to being at 1/2 or below. And then you can draw those bar chart, this histogram, where the bars of the histogram are so that the area of the bar is equal to the probability of that event happening, which we estimate as, in this case, 1/4, right? Because we have a pretty big sample of hairs that were cut, and you see that 1/4 of all the haircuts happen to be at this mark. The probability was 1/4 here, right? So that means that the height of this bar is 1/2, and its width is 1/2, and that's to make the area equal to 1/4. Similarly, we make the second bar equal in area to the probability of that occurrence. And we imagine that each hair somehow is cut independently. So in other words, how the barber cuts the first hair strand is not going to affect how the barber will cut the second piece of hair. Okay, so then you watch this a bit more carefully, and you notice the following, right? So then you see, well, let's suppose that I'm able to distinguish whether the cut was made between the scalp and 1/4 length, between 1/4 length and 2/4, between 2/4 and 3/4, between 3/4 and 4/4. And imagine that once you create the histogram, you get those blue bars. You can see the dots here. That's my previous estimate, and the blue bars are now representing the more accurate distribution of cuts. Right. So the cut happened to be here. So between 0 to 1/4, the probability was 1/16. The probability the hair is cut somewhere in here is the area of this rectangle, which is 1/4 times 1/4. Yeah, and then you can see the area of the hair being cut between 1/4 and 1/2 happens to be 1/4 multiplied by 3/4, or 3/16, and so on. Right. So you generate this histogram with thinner bars, and as you continue partitioning the intervals and carefully observing where each hair follicle, where each hair strand was cut, you have thinner and thinner bars, and they are like matches, like matchsticks. Eventually, they're so thin So imagine that what happens is that you realize those matchsticks or this very histogram with many very thin bars. The tips of those bars will line along this line, this green line, which happens to be y equals to 2 multiplied by x. So this green line is y equals to 2x. Can you imagine that, right? So here it's a very thick. It's kind of not easy to see why it should be under this line. But imagine then you make observations of whether hair was cut halfway between 0 and 1/4. And the other half, right? Or here halfway, or here halfway, right? And then you can see that the rectangles are just getting thinner and thinner and thinner, and you get twice as many of them. Each time you have the x-axis gets, and the x-axis they get half the thickness, and you have twice as many of them building the full histogram. Okay. So notice that at each step, the combined area of the bars adds up to 1 because the hair had to be cut somewhere. Okay, there was a cut made somewhere, so the area always adds up to 1. But as you construct those bars and they get thinner, eventually you might realize that we have like a very histogram of very thin rectangles with many rectangles building up the histogram, and each rectangle being very thin. And so you realize that full histogram looks like bars underneath the curve y equals to 2x, where x goes from 0 to 1. Okay, and then by the very construction, the probability questions you might have about this procedure are all settled entirely in terms of this curve y equals 2x. In particular, suppose I want to know that the cut, what's the probability that cut is made between some point A and some point B. I'll have an example below it, right? But if it's between some point A and some point B, it's just the integral from A to B of 2x dx. Right? Why is that? What is that? This integral is just nothing more than a fancy way of saying add. Right? So you are adding all the bars. The thickness of the bars is dx, and the height is 2 times x. Right? And the 2x times dx is the area of one such bar. Right? So here they are gross. So here dx is they're very big. Right? I'm sorry, I'm using the German word gross. Right? I forget. Gross means big in German, not ugly. So here the size is, so here dx is equal to 1/4, right? It's kind of not a very good dx. Dx has to be very thin. Dx is 1/4, and for this one, the height is 1/4. For this one, dx is 1/4, but the height is 3/4, and so on, right? So in general, if they're very thin, the thickness will be on the x-axis dx, and 2x will be the elevation of that rectangle, and 2x times dx is the area. And this means you add up all the rectangles from A to B. So you get b squared minus a squared as your probability. And in particular, what it means, for example, if that's the graph I generate, I have that probability that x is between 1/4 and 1/2 is the integral between 1/4 and 1/2 of 2x dx, which is 1/2 squared minus 1/4 squared, which ends up being 3/16. Okay, you understand how that is supposed to work? I hope the construction makes it clear, right? So this is in our example, we're asking for the probability that one particular hair strand is cut between 1/4 the distance to the root of the hair to 1/2 the distance to the root of the hair. What's the probability a cut is made in this interval? And that probability is 3/16. Okay, so this motivates the definition of what it means for a random variable to be continuous. So a random variable that takes real numbers is said to be continuous if there exists probability density function, which is a function from the domain of x to 0 to infinity, right? So it doesn't have to be, the elevation of this curve does not have to be less than 1. All that you just have this non-negative function, and all probability questions are settled in terms of that non-negative function. So for example, the probability that x is in the region B is just the integral over the region B of this function. Okay, and again, Why do you do that? It's by the very construction. So you can imagine that this curve is the outline traced by the tips of very, very thin rectangles. They're very, very thin, so you almost don't see, they're hair strand thin, they're very thin, right? So you don't see the thickness of them. The thickness is some dx. And then they are stuck underneath this curve, and their tips trace the outline of this curve. Make sure that I haven't lost you guys. And hello, John, it's very nice to see you. Hello, Isabella. Hello, Eli, and Shulamit, who disappeared. Okay, good. No, great. All right, so you all see, you understand the idea, right? It's pretty simple. So this is like a histogram containing a huge many rectangles, and the rectangles are extremely thin. And the tips of those rectangles are like the tips of matches of different elevations. And the tips of those matches are tracing the outline of this curve, which is called the density function of x, okay? So by the very construction of this curve, integrating underneath this curve gives you the probability, right? By its construction from, right? So here is first thing that I would hope you would find interesting. So here is the haircut paradox, right? You might wonder, how is it that you can go to a barber and get a haircut? And of course, today you cannot, right? Because everything is closed, right? But the paradox is not just due to the current situation. The paradox is perennial. So here is that question, right? So suppose that you go to that one barber whose density function happens to be 2x, right? So 2x over the interval from 0 to 1. So basically, if you give this barber one strand of your hair, the barber will cut it with a density function f of x equal to 2x, right? So that would be the density function determines the likelihood he cuts it in a particular point. Okay, so then I have the following questions for you. What is the probability that a particular hair that you present him will be cut halfway in the middle? Yeah.
Does that mean like exactly half?
Yes, exactly half, right? So don't look at me surprised. I want you to see if you can calculate. So Hugo, you came. Hugo is here. Wonderful. Welcome, Hugo. And you are right. It is 0, Hugo. And you see, it's 0. And let me ask you all the questions right away, right? So there is A, B, and C. So the probability that the barber will snip your hair exactly halfway between the scalp and the tip is 0. What about 7 over 8? Right? So in other words, here you just measure 8 pieces of the hair, you move up, and you snip away the last 8. What's the likelihood that happens?
0, 2.
0, 2. Oh, what about any point, right? You take a hair, just any point B. So, you know,
1.
B can, any point B, just for any particular point B.
Oh, 0.
0. So any number, you know, the hair is between 0 and 1. Any number, the probability that the hair is cut there is 0. Doesn't it bother you? So how are you getting a haircut? Right? The probability. It's impossible to get a haircut, exactly, right? So another student from my other class, he already does the haircut on his own. That's a good idea, right? So consider also doing surgery on your own, right? It's also a useful skill to know. My friend wants to go David Crockett. So how is that possible? Think about it before I give you my solution to it. Right? Just think about it.
Because we calculate the area under the density function, and 1 point doesn't give us any area. It's like
that's technical. Yes, You're absolutely correct. Technically speaking, you can prove that that the probability is 0 for any point, right? So nothing special about 1/2 or any other point. So I'm saying 1/2 is a particular point where you might want to know the probability. 7/8 is another point where you might want to know the probability. But if you examine any of the infinite points individually, you find that the probability that the individual point you selected is the place of the place where the hair was cut. It's 0, right? How could that be? Then how do you get a haircut? Doesn't it mean that you know 0 probability at 1/2 0, probability at 7/8 is 0? So you're adding a bunch of zeros, right? So how can a hair be cut? Yeah, so Andrew is just taking the physicist's way out, and he's saying, well, it's a real world quantity, and it's impossible to measure a real world quantity, right? Exactly, right? You cannot have a precise measurement of any quantity, right? So he says, let's say 5.0, it's just an approximation of 4.95 and 5.05. So it's a number in between. Sure, but still the question is, right? So when you make a cut, measured or not, you cut it at exactly 1 point. I mean, you might try to go and fight against the idea that real numbers model real space or real universe at all. But for a moment, if you do not do that, right, the hair, whether you can predict it or not, is cut at a particular point, right? At an exact point B. It happens, right? So if you look at the hair, you cut it somewhere. It happens to be at some point B. How could it be that the probability it's cut at any point equal to 0? Interesting. Yes, I would say that when I think of mathematics, it also it always feels like Chinese to me. Oh, it's so nice to see you guys, all of you, right? More faces than I expected, so good. Great. So I do like what Andrew suggested. I like it very much, right? But I wonder if you can give yet another solution, right? That I suggest a similar thing here. All right, I guess we are ready. Okay, so I would say this. Remember, guys, I mentioned to you that if probability of some outcome is 0, it does not mean it doesn't happen, right? And this is the least artificial scenario in which I know this to be the case, right? So just because the probability of one outcome or another is 0 does not at all mean that it doesn't happen. It just means it happens extremely not frequently. So, compared if you were to perform a trial, right, many trials, maybe you are lucky enough to see the haircut at 1/2, but that's very, very, if you then, you will never see a repetition of it, right? If somehow by some very strange, you know, collusion of events, you do see the haircut at 1/2, you will not see it on the second trial, third trial, fourth trial, possibly you will never see it ever. I would say you will never actually see the 1/2 as well, because it just, many, many stars have to match, okay? So here is the solution in general, right? So if I have y, and y has a density function f of y, then the probability that y equals to some number b is just the integral from b to b of fy dy. And that has to be 0, right? This is 0. Because again, by geometry, you just know that thickness is 0, and 0 times whatever height is 0. And by integration, just, you know, you take antiderivative of this little f, you plug b, and you subtract the same function at b, so they cancel each other and reduce to 0. Okay, so again, right, so I mentioned that if you think that probability that y equals b is just the limit as it goes to infinity, I basically cut a bunch of hairs, more and more and more hairs, and I consider how many times do I get exactly b. So it will be the number of times in my trials that I get exactly b divided by n. This number will surely go to 0. So it could even be that that the particular outcome here happens many times, even infinitely many times, but the frequency will be very low, and on the limit it will go to 0, right? But by the very setup, you see to figure out that that y equals to b, you have to have lots and lots of numbers matched, like Andrew suggested. So for example, every real number, if you think of 1/2 can be represented as 0.5 followed by infinitely many zeros. You understand? So every real number is an infinite string of digits. So in base 10, it's really a geometric series type of thing, right? Every real number is just an infinite string of digits. And to truly get 1/2, you have to match all the infinitely many digits, which is quite hard to do. So for example, if you have a calculator, right? If you have a calculator that can display 8 digits, and is it 0 probability that over the 8 digits you would see 1/2? So 1/2 might look to you like this. 8 digits, you see 0.5 and a bunch of zeros there, right? And maybe afterwards, what the calculator truncates, maybe afterwards there are non-zero numbers. We don't know. The calculator gave you 8 digits. And that happens to be the integral from 1/2 to 1/2 plus 10 to the minus 8 of 2 to the x. And that can be just approximated, because this is such a thin distance, that can be simply approximated as the height at 1/2 multiplied by the thickness, by dx, which is simply 10 to the minus 8. And that's a very small probability, but it's not a 0 probability, right? 10 to the minus 8 is very small, but not 0. So that could potentially be witnessed. So 1/2 up to 8 digits, or even a half to more digits, is not 0. But witnessing 1/2 entirely, you might say, is impossible. Okay, so another way to say that is just, well, there is no device, there is nothing in your everyday life that allows you to see a number through infinity. If you believe in God, maybe only God can see 1/2 to infinity, all the digits, right? There are infinitely many digits. 0.5 followed by tons of zeros unending. So nothing in your world ever works like it. Okay, so you might say, well, it's impossible to see y equal to exactly b, because that implies that I'm seeing infinitely many digits, but I never see infinitely many digits. But so my explanation, do you agree with it, or you think, well, you just don't want to tell me, you're polite? You get my explanation? Good. Shake your head. Cool. Yeah, so it's not so terribly paradoxical afterwards, right? So you can either imagine that, well, witnessing up to 8 digits or up to any number of digits, that's very possible, although unlikely if there are many digits. And the other, and it's impossible to see the full string of digits. The other way to think of it is that, well, it could happen that somehow I get exactly 1/2. Maybe I don't represent 1/2 in terms of the digits. I actually see 1 divided by 2 as my answer, right? And then if that's the way I think of it, then maybe 1/2 happens, but it happens with frequency that approaches 0. In other words, when you simulate this experiment in practice, you will never see the numbers repeat. So whatever number in the simulation that comes out, let's say the number 3/4 comes out, you will never see that number again. And here is just to see if you have a feeling for the distribution. So a girl wants to get a haircut. Andrew asked a very nice question. How come you never see it again? Those that you, so it's, I don't know if I can make it truly polite, poetic, but when you meet, when you meet somebody, usually it's one moment and never again, because universe is infinite, right? So it's the same thing here. It's just that when things are so rare, you collide with something, even with people, right? You lose a person, you never ever find them again. So a girl wants to get a haircut. Not only that, I mean, you see, I restricted myself because I go crazy about it. When people mention something, I want to quote something that I know, but then I figure, well, you don't understand it, and that will be embarrassing. So I restrained myself from quoting something that I immediately thought it was in Hebrew. So a girl, I might send you a link in case you want to listen how it sounds. A girl wants to get a haircut. She can go to one of 3 barbers. The barbers cut each individual hair strand in accordance with the following density functions. Okay, so here are the density functions. Okay, so you want to get a haircut. Which barber do you select and why? Or in particular, just tell me what would the girl look like after the haircut by barber 1, barber 2, and barber 3. She has long hair. Draw a picture or describe it if you don't want to draw a picture.
She better to go with barber number 3.
Well, and why?
Because the density function is more above like half length.
Right. So
long hair, and she wants to get a long haircut. Maybe that barber has a better.
Right.
Yeah.
But that's brilliant, right? So of course, I mean, I would say if you have a choice, go with either barber 1 or barber 3. I mean, if you want your hair very short, go with barber 1. Because this barber tends to cut hair like in the military, close to the base, right? And this barber tends to leave most of the hair. But this barber kind of cannot decide what he likes. It's a 2-hump camel, right? So he sometimes cuts the hair very close to the base, and sometimes cuts it very far from the base, which means that's not a very skillful barber, right? So if the girl has this nice flowing hair, after barber 1, she will look like this. After barber 3, essentially just shorter hair, but after barber 2, my God, some hairs are short, some hairs are long, terrible haircut. Okay, so wonderful. That's just simple, right? Now let's do calculations, right? So here is your first problem. So we have some random variable x, and it's continuous, and the density function is given by f of x equal to cx squared, where x is between 0 and 2. And we have to determine first what is c, and then compute the probability that x is between 1 and 2. Okay, would you go ahead and please solve and tell me what is c, and calculate the probability that x is between 1 and 2. C equals to 1/4. Well, let's see, right? So not quite 1/4. Now, what's the idea? Most importantly is the idea, right? Calculations are less significant.
The area under the density function should be, the cumulative value should be 1. So,
Yes. X can only take numbers between 0 and 2. So when you simulate, when you actually run the simulation, a number between 0 and 2 will come out, right?
if
So,
you input 2,
yeah, so you integrate from 0 to 2, this function, and you want to set it equal to 1, and that will allow you to solve for C. So that's what we do. We integrate in general from -infinity to infinity, but of course, most of them are 0. So it's really from 0 to 2. Right? This is just in general to indicate that, well, values, this is the second part, tells you that the function is defined over all real numbers. You can always assume the function is defined over all real numbers. It's just for most numbers, it's 0. So it's just integral from 0 to 2 of cx squared. And that becomes c over 3 times x cubed. I just took the antiderivative of that, evaluated from 0 to 2. And I get c times 8 over 3. And therefore, c equals to 3 over 8. Because this number has to be equal to 1. Good? Now, calculating the probability that x takes the number between 1 and 2 is simply the integral between 1 and 2 of 3/8x squared. Right? And then we get that the answer is 7 over 8. It's just integration. Nothing so special. Most importantly from this class is that you understand why I integrate. It's pretty much by the way I set it up, right? I just did, what I'm doing is I'm adding many very thin rectangles in a very big histogram. So in the histogram, the rectangles are all very thin, and there are very many of them. Good? So that's why it's area under the curve. Yeah. In practice, I suppose, right? I never bothered ever seeing how such things are generated. But in practice, what you do is you make a big sample, right? You generate a bunch of x's. So you just run the simulation a lot of times, and then you stack up outcomes over thin ranges together, and you get the bar charts and the outline roughly you interpolate, and that will be your density curve. Good. So here is another example of the same type. So you have a computer that you keep running, and let's say the density function that it will run for X amount of time is lambda e to the minus X divided by 100. Okay, so that means simply, how long it will run before the computer freezes. So I want you to calculate the probability the computer will work between 50 and 150 hours.
Will we be integrating this from 0 to infinity?
First, right? Because I need to know the lambda, right? I need a number here. So when I integrate it first from 0 to infinity, correct, Isabel? exponent, well, it's e to the power of minus x over 100. Lambda multiplied by it. It's more like Calc 1, Calc 2 really right now. It's not nothing so interesting. But it will be Calc 3, guys. Even today, maybe. Isabella, no. This, by the way, is, I'm not sure if we'll have time to cover it, it's the exponential random variable. I like it because it's memoryless. It doesn't remember anything, just like me. Man, yeah, I wonder what sort of thing you imagined it to be. You should have taken Calc 2 with me. All right, so let's do it together. Guys, it's a constant. You move it out, you integrate e to the power of minus x over 100, right? E to any power is just e to that power. So you just get e to the minus x over 100. But because, you know, when I take the derivative of, by chain rule of this expression, it drops down a minus 1 over 100, which means we have to meet it with 100, with minus 100 to be more precise, right? So you see what happens, right? So I guess the antiderivative. The antiderivative, I guess, is e to the minus x over 100. And that's not quite a correct guess, because when I differentiate, a minus 1 divided by 100 pops out, which means I need to compensate by multiplying by minus 100. Yeah? So we have this expression. Now, when I put in 0 and infinity, at infinity, this is 0. So I get simply lambda times 100 equal to 1, which means lambda equals to 1 divided by 100. Good? Simpler than one could imagine, yes? And now if I need to calculate the probability that x is between 50 and 150, that's just the integral from 50 to 150 of 1 over 100 e to the minus x over 100 dx. And that is just this expression, which upon plugging in, it happens to be e to the minus 1/2 minus e to the minus 3/2. It's roughly, if I remember, 38%. Okay? So in this computer will function between 50 to 150 hours, you know, without being turned off and without crashing, with this probability. So we spoke before about cumulative distributions. I must confess, I have no idea what's the use of cumulative distributions for discrete random variables, but they're obviously useful for continuous random variables for the following reason. Okay, so first of all, what is the cumulative distribution? It means that it's just the probability that x is taking a value at a or less than A for any A, right? So, and we denote it by capital F. Okay, we had the little case f that was the PDF or probability density function. CDF is the cumulative distribution function, and f at A, for example, for any A in the domain of X, will be the probability that X is less than or equal to this A, which is the integral from minus infinity to A of little f dx. Yeah. So what's the use of it? One use is that I can convert the cumulative distribution quickly to a density function. You will see below in examples why you would want to do that. Okay, so you do that by taking the derivative. Let's say a little f a equals to the derivative with respect to a of this integral, which is the derivative with respect to a of the cumulative distribution function. If you remember, this is the fundamental theorem of calculus. And it says many rather interesting things, right? So, you know, why do you use the fundamental theorem of calculus? For example, when you claim that, the difference between potential energy is work, that's in physics, and in probability, it means it allows you to get a density function. Here is how I know that. Well, the derivative of the cumulative distribution, by the definition of the derivative, is limit as h goes to 0 of the difference multiplied by 1 over h. Right? That's the definition of a derivative for any function. Correct, guys? And if I just work it out, I take limit as h goes to 0. 1 over h, it's the integral from minus infinity to a plus h minus the integral from minus infinity to a, which clearly just this is gathering area all the way up to a plus h, and this is gathering area all the way to a. So when I cancel them out, I just get the area from a to a plus h of little f times 1 over h, right? Which I can, this is very, very simple. Because the function is continuous, because little f is continuous, I can replace this integral where h is small enough by fa times h. Do you see why I can do that? Because think about it, right? Of course, I made h rather big, but that's only for you to see. Imagine that h is very small. Now, you can imagine that I think of matches. And of course, they're not of the same length, but I always imagine lots of matches, right? So the matches here have very similar elevation. So as h is getting smaller, the elevation of each match is essentially that which equals to f of a, because the function is continuous, right? So matches of nearly identical length are close together. And as you move towards a, the matches here will be getting more and more of the same length. You cannot distinguish between them. So what do you have here? So the integral is very similar to an integral of a constant function, or to the area of a rectangle, whatever you like calling it, right? So if h were smaller, let's say h already happened to be here, all the possible x's in this interval would have been essentially of the same elevation, and the area would have been width, which is h, times height, which is f of a. You follow? So this integral is essentially, when h is really small, is essentially fa times h, right? And when I multiply it by 1 over h, essentially I'm taking a limit as h goes to 0 of f of a, which does not react to h. So I get that in the limit it equals to f of a. You follow? It's there is in the fundamental theorem of calculus, actually, it's very, very clever, but once you understand what's the mechanism behind it, the mechanism behind it is very simply is that you realize that to get the elevation, you just divide the rectangle by its width. So you have the area of the rectangle divided by the width. So in the continuous function, when h is very small, the area is essentially that of a rectangle, because all the elevations, they look alike. Yeah, you can make it rigorous, you can have uniform continuity and all that stuff from analysis, but the idea is that the matches close to A are essentially of the same elevation, and therefore what you're tracing here is a rectangle. This is essentially a rectangle. You don't believe it only because h is not that small. Good? Yeah. And here is why density, why cumulative distribution is useful. Suppose I had this problem. So I have x, and it's a random variable that has a density function little f x. And then I defined y to be twice x. What is the density function of y? It's x is continuous, so this would be a continuous random variable, right? What is the corresponding density function? And because of the fundamental theorem of calculus, I can use the cumulative distribution to answer this problem. So what I can say is, well, okay, I will need to differentiate the cumulative distribution of y. And the cumulative distribution of y at the point A is the probability that y is less than or equal to A, which is the probability that 2x is less than or equal to A, which is the probability that x is less than A over 2, which is the cumulative distribution function of x, but at a different point, at A divided by 2. Yes? So you see, I easily can move from one cumulative distribution to another in this case. It's not so easy to directly move from one density to another. It seems easier to move from one cumulative distribution to another. And then what is the density function for y? It's just the derivative of the cumulative distribution of y, which is the derivative of the cumulative distribution of x evaluated at A over 2. And how do I take derivative of a compositional function? The derivative of big fx is little fx. And the derivative of what's inside is 1/2. So by chain rule, it's derivative of big F evaluated at A over 2 multiplied by the derivative of what's inside, which is by 1/2. So I'm hoping this is known. You know it very well, guys, right? You are good. You haven't taken calculus with me, except I think for one person here, but you know this information. So so I got my density function. You see, in terms of the density function of x. Let's see if you can solve this problem, please. So I hope you can see everything on my screen. Suppose that x has the following distribution. So x can take values between 0 and 2, and it has no preference which values it takes. That means that the density function is everywhere the same, right? So we have values from 0 to 2, and the density function is 1/2. I want you to find the density function for y, where y equals to 1 divided by x. See if you can do that. Understand? I want you to find little fy. How is 1 over x distributed? Okay, cool, Andrew. Possibly, I don't remember, but we'll see below. All right, so let's do it together. Or you still want to solve it? No? One feels smart when one solves it for the first time, right? Afterwards, trivial. So here is how you begin, okay? Reminds you of calculus as well, right? So capital Fy of A is the probability that y is less than A. And that is the same as the probability of 1 over x less than A, because that's what y is, you see? So very quick transition from speaking about y to speaking about 1 over x, right? And what is that? That's I need to get x something, because that's all I know. I know the density for x. So I take reciprocals and I get that x is bigger than 1 over A, correct? They are positive numbers, you see. So y has to be a positive number, obviously, right? Because y is 1 over x and x is between 0 and 2. So if 1 over x is less than A, x must be bigger than 1 over A. Yeah. And yes, and this is not a function I like to deal with. So, but because we have probabilities, this equals to 1 minus the probability that x is less than or equal to A. By the way, for continuous random variables, you can always be free about saying less than equal to a number or less than a number strictly, because the probability of getting exactly the number is always 0. So it's 1 minus the probability that x is less than or equal to 1 over A, which is 1 minus the cumulative distribution for x at 1 over A. And so I take the derivative of the cumulative distribution of y to get the density at y. And that will be just the derivative of this expression, which ends up being 1 over A squared times f of 1 over A. Why is that? Because look at it, there is a minus. Yes, right? So there is a minus, right? And when I take the derivative of the inside, I'll get minus 1 over A squared. So the minuses cross away. And I just get when I take the derivative of capital F, I get lowercase f, because when I take the derivative of cumulative distribution, I get density. So the cumulative distribution, Andrew, of course, it's the integral from minus infinity to the particular point A. So you can always obtain the cumulative distribution if you know the density function. Yeah. So, and here is the result. I wrote it in A to be convenient, but you can write it in terms of y. So what values can y take? If x takes numbers between 0 and 2, the smallest number y can take is 1/2. And of course, as x gets closer to 0, y grows. And so the value of y can be anywhere between 1/2 to infinity. And the function that I get, look at it, right? So I evaluate f at whatever number, right? So that would be 1/2 times 1 over y squared. So I get 1 over 2y squared is my density. Okay, you see I moved from, yes, It's kind of like in Back to the Future. You are my density, if you remember. Right, so you get the density from the cumulative distribution. All right, so again, your turn. Here is x. Its density function is given by e to the minus x for x between 0 and infinity. I want you to tell me what is the density function of y, where y equals to e to the x. Calculate. You can all do it. You too, Norosima. You can do it. I believe in you. Yes, you're right, Andrew, I think, and then just simplify it, because we know what is fx. All right, let's see how that's going together. Yeah. So the very first step is, you might prefer a different letter, not X, not Y. So you say cumulative distribution of Y at A. That's the probability Y is less than A, which is the probability e to the X is less than A, which is the probability X. I just take logarithms of both sides. X less than ln of A, which ends up it's the cumulative distribution of X evaluated at ln A. And so to get the density function, I differentiate, and I get, differentiating this, it's the derivative of the big F is little f. Inside we find ln, and then we multiply by 1 over A, the derivative of ln. So this represents the cumulative, this represents the density of Y. Okay. Now, what is fx of ln A? Well, it's e to the power of this number. So it's e to the power of minus ln A, which is the same as 1 over e to the ln A, and they are inverses of one another. So this is just 1 over A. So this number is 1 over A. So we have 1 over A squared. So that means that my function for Y, my density function for Y, it's just 1 over Y squared for Y equal to a number between minus infinity and infinity, right? Because if X is between 0 and infinity, did I make a mistake here? Could be. So I think I made a mistake. This should not be minus infinity. There should be what? So this should be. It should be from Y should be between what? Between. Damn it. So it's this, right? So e to the x, right? E to the x is a number between 0 and infinity. So it should be between 1 and infinity. Right? X can be, Y can be a number between 1 and infinity. So what I wrote over here is wrong. It should be 1, yes? You understand how I figure it out, right? So what values can X take? It takes values bigger than 0 and less than infinity. So what would be the corresponding values of e to the x? It's just the same number raised to the power that came out. So e raised to a number between 0 and infinity will be a number between 1 and infinity. So this has to be 1. Make sure you correct it. And one way to verify you're right, integrate this function from 1 to infinity. It has to give you 1. Yeah. From minus infinity to infinity, obviously it's not continuous. It's 0, right? So it's a mistake. So the values that can be taken is y between 1 and infinity, and this is 1 over y squared. Good. So what else do we have here? So next topic is expectation and variance of continuous random variables. So the first thing to note is that I can figure out the definition for expected value very simply, because when I see a continuous random variable, I regard it as a discrete random variable where the x's are just very densely packed together, right? So the probability of this particular x is just the area of a very thin rectangle. I just made it exaggeratedly big. It's just a very, very thin rectangle. So between x and x plus dx, right? So the expected value of that corresponding discrete random variable, as we thought before, would be the summation over all the x of the outcome, the score, multiplied by the probability. And the probability is the area of the rectangle. So it's little f x dx. So this part represents the probability, and this represents the value, right? So the expected value of x will be pretty much this, which amounts to adding up over all possible x's multiplied by the probabilities, which is the integral from minus infinity to infinity x fx dx. Definition makes sense, right? So in other words, I regard a continuous random variable as a discrete random variable where the outcomes are very many and they are densely packed together. So it looks to me like it's continuous, right? That's in essence how I think of continuous random variables, and then many properties can be intuitive if you know them for discrete random variables. So maybe you do this one last favor to me, right? So this is the barber, the haircut function. So what's the expected value? In other words, what's the expected place where you will see the cut made? F of x equals to 2x if x is between 0 and 1. Calculate the expected value, please. Are we just dividing the integral by the range? Well, be careful. I'm not exactly sure what you mean dividing the integral by the range. What I imagine is that if x takes values between, let's say, a and b, I imagine dividing this interval into many segments, many thin rectangles, which will divide the interval into segments of the form x and x plus dx. So the probability that we have outcome x is just the area of this rectangle, which will be very thin if you do it properly. Two-thirds, very likely. Thank you, Isabel. All right, so the answer is 2/3. So we just integrate x multiplied by 2x dx, and we get 2/3. Okay. More importantly, I mean, I'm sure many of you remember integration, at least in its basic form. So obviously, if you know to do that, you get 2/3. Do you understand why expected value is defined to be the integral from -infinity to infinity of x times f of x dx? That is what I would like you to understand and think about. Okay, why is that a correct definition? And I suppose what our time is up. You are free to stay and ask me questions if you have any, but the time is up. Some of you have to go to the next class. Goodbye if you are not staying.
Thank you.
Thank you.
GTG. What is GTG? Ah, good. We learned so many new things. Apparently, toddlers, they communicate in some secret language. They just type symbols and they understand it. Somebody posted it. So don't worry, you are getting old too, not just me. TTY. TTY sounds like something not polite to me. Okay. Wonderful. TY is thank you, right? All right, guys. Again, very nice talking to you. If you have questions, stay. I'm just waiting. So I think some people stayed. So those that stayed, how can I help you? What can I do for you?
Could we, like, you were just talking about like why the expected value is the integral, you know, of x f of x. Could we explore the reasoning?
Yes, I will try. Right. So again, right, the distinction between summation in integration is only nominal, right? What is this symbol? This S stands for summa or sum, right? So it's a very similar symbol to this, really. At least it has the same meaning. How do I calculate area? So if I have integral from a to b, fx dx, the notation is supposed to remind me that all I'm doing is adding the areas of very thin rectangles. The dx means that the base of the rectangle, this one, is supposed to be very thin, right? So not like what I drew here, really, so what you're seeing is a bunch of matches, right? So what I'm doing is adding the areas of the matches. So imagine that the matches, so imagine this segment is so thin that pretty much, well, let's say maybe there are 1,000 different x's here, right? So I have a plus 1,000, a plus 2 times 1,000, a plus 3 times 1,000. That would look very thin, right? So what I'm doing is I'm moving, let's say I'm plugging a plus, let's say n times 1,000, which will give me this elevation, and multiply it by dx, and that will be the probability, okay? So when I calculate expected value, it's just going to be, let's say, for a generic point is going to be at some place x. So it's going to be x multiplied by the probability, by f of x dx, right? So x multiplied by its probability, f of x dx, will be the part of the expected value which calculates the ratio of outcomes of the form x. Yeah?
And small f of x is the PDF,
Small,
right?
The PDF, right? Small f of x is just the elevation. So at this x, how tall is this match? This is how tall is this match, right? So I need to know how tall is this match, because then I multiply by the thickness, which I always decide to make uniform, right? I'm free to decide to make the thickness for all the matches the same. Yeah, I'm not forced to do that, but that's fine to do it, right? So fx dx only means the probability, which is the length of the match times its thickness. And you see, if I imagine discrete many x, so imagine that I just wrote it as x, but really what it is, it's a, maybe the next is a plus 1 over 1,000, next is a plus 2 over 1,000, right? So I'm just moving through only 1,000 different numbers. And if I multiply those numbers by their corresponding probabilities, I will essentially get the expected value of a very similar but discrete random variable, right? Continuous might be thought of as a limit of a discrete. In other words, in the discrete, you have only finitely many outcomes, or countably infinitely many outcomes. But a continuous random variable, will have uncountably many possible outcomes.
I'm wondering what we would do if we started with the cumulative distribution and tried to obtain the expected value from that.
If we start with cumulative distribution, then you take the derivative of it. So it would be the integral of the particular score multiplied by the derivative of the cumulative distribution. And then you integrate it.
Okay, yeah. So you would get, you would always come back to PDF first.
Well, I mean, do you have to come? I mean, sometimes you will see some sort of shortcut. So you will see later that, for example, the expected value here, it's the integral from, let's say, x to f of x, ends up being the probability that x is bigger than a particular value, right? So it's 1 minus the. So this part can be thought of in a way you can change and make it look like I do it lower in the notes, roughly speaking, right? So by change of variables, you see here is the expected value. By change of variables, I can see here is the expected value for y. I do this, and by changing the order of integration, I end up integrating 0 to infinity. Probability y is bigger than x, which is the same as probability y bigger than y, right? So I can, instead of having the y in front, I can just say, well, let's just the integral of 1 minus the cumulative distribution, because this is 1 minus cumulative distribution. Okay, so I can, instead of having, as we have over here, x times little fx, I might have, I can replace it and write probability, or just, sorry, 1 minus the cumulative distribution. It ends up being the same. Really interesting, right? So, so what you asked here, right? So in this, instead of doing expected value of x, I can integrate 1 minus the cumulative distribution here. Instead of both x and f of x, replace that by 1 minus capital Fx. And if I can integrate that, that will also give me the expected value.
Thanks.
Yes, great. That's a good question, Andrew, right? So, and I mentioned another thing to you, right? I mentioned it in passing. Remember, you asked about Poisson random variables. We found that they have, yeah. So you remember you asked me, is any distribution where the variance and expected value are the same, is it always Poisson? And the answer is manifestly no. I think you can try, let's say, you can try distribution that you know, might equal to, say, 1 with probability 1, 2 with probability, or sorry, maybe. Basically, you can make you can have values 0 and 2, right? 0, 1, and 2. Let's say each with probability 1/3. Let's say 0 probability 1/3, 1 with probability 1/3, and 2 with probability 1/3. So this random variable only generates 3 possibilities, and I think that would be an example of a random variable that's its expected value is and variance are the same. Or just avoid 1, just make it 1/2 at 0 and 1/2 at 2. Right? The expected value is 1/2 of 2. That's easy, right? 1/2 of 0, 1/2 of 2. Expected value is 1. I think variance would also be 1. I think, right? I haven't calculated, but yeah, I'm pretty sure in general that you know, you have plenty of distributions that are that have the same variance as expected value, and they are not, you know, they are not Poisson. Right? If I made an error, I said I thought so easy, didn't bother calculating. I think I'm right. Right? Variance would be what? It will be x minus 1 squared, right? Because so what's x minus 1? X is so x minus 1 squared is just yeah, x minus 1 squared. The expected value of that can be calculated as 0 minus 1 squared plus 2 minus 1 squared, and all of it divided by 2, right? So what you get is you get 1 plus 1 divided by 2, you again get 1. No? All right, great.
Yeah, cool.
Cool. All right, then. Have a good one. Enjoy the rest of the day. Go out. You don't look like you see a lot of sunlight.
It's going down.
Yeah. Take care.